Make it fit.
Idiot. All right, so I want to do two things today. First, I want to do a little review of the graphs of quadratic functions in general form. Okay, let's call this though. I know that the textbook we're working out of, the online textbook, calls this general form, but that's just weird. I mean, there's never been another textbook I've seen that calls it general form. Let's call it standard form. Standard form and general form are the same thing. So if we want to graph a function that's in general form, let's just go through an example like that. Okay, so what do, right? We know that when it's in general form like this, we can't just go right to the graph, right? We can if it's in vertex form, right? If we were able to put this into vertex form, and what's vertex form? F of x equals what? A times. Okay, how do we put the h in? The quantity x
minus h squared plus k.
Okay, that's vertex form because we can see the vertex. The vertex is at hk, and so we can see the values of h and k just right in the function, right? So if it was in that, it's a piece of cake, and that was way back in, I don't know, 3.4 maybe, no, 3.3 I think. Section 3.3 we did that. Okay, but now we're going to go straight from standard form. So how do we do that? We have to, in order to be able to graph this thing, we need to know where the vertex is and we need to know what the vertical dilation is, right? So how do we do that? What's A, first of all?
-3.
Yeah, we know right away that A is -3. It's right there. Okay. How do we find H and K? So how do we find H?
Negative b over 2 times a.
Good, negative b over 2a. So if we plug that stuff in, if b is -6, what's negative b? 6. Over 2 times, and you already told me a is -3, so 6 divided by 2 times -3, what's that?
-6.
6 over -6 is -1, good. So we got h, how do I find k?
Yeah,
Plug it in?
Yeah,
I just plug it into the function. So I'm going to plug -1 into the function up here. Every place I have an x, I'm going to put a -1 in parentheses, right? So it's equal to -3 times -1 quantity squared minus 6 times -1 plus 3. Well, what's -1 squared? Positive 1 times -3. Thank you. -3, right? -6 times -1 plus 6 plus 3. What's -3 plus 6 plus 3? 6. Okay? So then we also know that the vertex, hk, is at -3, 6, right? And so now to graph this thing, we know that's where we're going to start, right? The vertex is at -3, positive 6. So the vertex goes right there. Agreed? Okay, at -3, -6, or positive 6. Wasn't it -3? Yeah, -3, positive 6. Okay? Now, what about the curve from there, though? This is where we need to know what A is, right? Because A is going to be our vertical dilation factor. This is where people are still having a little bit of an issue, so I want to go through this in a slightly different way today. Just give you another look at how to conceptualize this. So let's make a table. The table is going to have, the first column is just going to be delta x, which is going to stand for the horizontal distance from the vertex. Let's get all the phones away completely, please. So this column, horizontal distance from HK. That's what that column's doing, right? This is going to be for our parent graph, the vertical distance from HK. Okay, make sense? So how far we're going over compared to how far we're going up. So that's what that column is. We can fill those out right now. If we go 1 to the right, let's do a couple of these. What if we go 1 to the right, or 2 to the right, or 3 to the right, or 4 to the right? If I go 1 to the right, how far, my horizontal distance from the vertex is 1. For the parent graph, what's my vertical distance? 1. Good, we get that just from 1 squared, right? So we're just going to square the horizontal distance. So 1 squared equals 1. What about for 2?
4,
For 3?
9,
16,
4.
26, 29,
Good.
41.
So those are the values, those are the amounts that I would go up vertically for these horizontal distances. Okay, what's A?
-3.
-3. Okay, what does A do? Well, A just multiplies the parent vertical distances to give us the dilated vertical distances, right? So if we're going to multiply by -3, it was -3, right? Then delta y, the dilated delta y. So our dilated vertical distance is just A times the parent vertical distance, right? So what is it going to be for a horizontal distance of 1? What is our dilated vertical distance going to be? -3 is our vertical dilation factor times our parent graph vertical distance. So I get -3. What about for 2?
-6.
No,
-3.
No.
-12.
-12. I get 4 times -3 is -12, and then -27, and they get big, right? Okay, so let's compare what the parent graph looks like to what our graph needs to look like. So the parent graph, we know, we go over 1, we're going up 1, right? If we go over 2, we're going up 4, so 1, 2, 3, 4. Right, so that one looks pretty, we're used to this graph. There's our parent graph, right? What's our graph look like? So we're going to go over 1 and up -3.
Down 3.
So we're going down 3. Right? We go over 2, and we go down 12. So there, right? So look at our transformed graph, our dilated graph. It's tall and skinny, right? It's been stretched by a factor of 3. The negative means it's been flipped, and the vertex is at 3, 6. Okay? That makes sense? That help with what A does? All A is doing is just multiplying the normal changes in Y by A to give you the dilated changes in Y. Okay? Let's try this in the other direction. Let's try, what about something like this? So we'll do one's fraction here. So what about this one now? This time we want to start with the graph, and we want to write the function in that form, right? So what are we going to have to do? We're going to have to retrace our steps, because this is just the opposite of what we did in the first example. So the first example, we started with general form or standard form. We found the values of A and H and K, which is like putting it in vertex form. And then from there, we made the graph. So if we're going to retrace the steps, we're going to start with the graph. We're going to go back to vertex form. And then we'll just transform vertex form into standard form, right? Okay, so let's try one of those. Okay, so from the graph, what are the values of H and K?
-6 and -4.
Okay, good. So that point right there has coordinates -6, -4. So we know HK have the values -6 and -4. Okay, what about A though? That's the part that's maybe a little bit harder. So let's go back to our graph again. So once again, let's take horizontal distances of 1 or 2 or 3 or 4. What's the parent graph distance going to be? Well, if we horizontally go by 1, you told me we go vertically. We our vertical distance is 1, right? Horizontal distance of 2 from the vertex, vertical distance of 4, 3 and 9, 4 and 16, right? Okay, so what do we have here though? Let's look at this example. So they gave us one reference point to use. Now this is not the parent graph, right? This is the dilated graph. We're trying to write the equation for the dilated graph. Okay, so for this point right here, between the vertex and this point, what is the horizontal distance? Because you think about an ant having to walk from the vertex to this point. How far does he have to walk horizontally and how far vertically?
3, 6.
Okay, so he's walking horizontally by 3, right? And the vertical distance, if we go over by 3,
Up by 6.
we're going up by 6. Okay? So that's this row right here, isn't it? Right? Horizontal distance of 3, the vertical distance is 6 on the dilated graph. So then what does A have to be? Well, we know that A is what we multiply by the parent value to get the dilated value, right? So 6 equals A times 9. Another way to think about that would be, if I want to solve for A, I could just divide each of these through both sides of this little equation by delta y, right? And I would just get A equals blue delta y over red delta y. So dilated delta y over parent, undilated delta y. So what's that give us here?
2/3.
Yeah, A is going to equal the undilated value, or the dilated value, sorry, is 6. And the undilated value is 9. And so A equals 2/3 if I reduce that, right? Do I see that? Okay. Why did we use this point? Why didn't we use like this point right here, go over 2? That's not very convenient, because if I go over 2, the dilated vertical distance is some fraction, and I can't see, I don't know accurately what it is. This one I know accurately though, because it goes exactly over 3 and up exactly 6, right? So we're going to use that row. Okay, so now we know what A is. H is -6, K is -4, and A is 2/3, right?
Yeah.
So all we have to do then is convert from vertex form into standard form, and we're done. And that's not hard. So we start with vertex form, not y, f of x. F of x equals what?
2/3.
2/3. A goes there, right? So 2/3 times x minus -6, so plus 6 squared plus -4, so -4, right? And my goal is just to get that down to standard form. F of x equals ax squared plus bx plus c, right? How do I do that? Right?
Exponents at first.
Yeah, this is just algebra now. All we're doing is simplifying, right? This is a simpler form than that is. Ax squared plus bx plus c is the simplest way we can write it, the standard way of writing it, simplest way we can do it. This way is convenient for graphing, but it's kind of difficult, right? So we just have to follow regular order of operations. And we're just going to go down like we normally would from the top to get from here down to there. Just simplify. So what's the first thing we do? Can we do anything inside the parentheses? No, can't do anything there. So the first step is going to be right here, exponents, right? Well, there's my exponent I have to deal with. I've got something squared, right? So how do I deal with that?
Distribute the exponent.
I can't just distribute the exponent because this stuff's being added. I've got to do something. It's a little harder than that. So if I've got x plus 6 squared, I could just write it as x plus 6 times x plus 6 and distribute it out and add like terms. But remember the trick I showed you. It's a good trick, right? The trick is if you instead think about the pattern a plus b squared. What's the pattern? A plus b squared, if I expand that out, it's always going to be what?
A squared plus B squared.
A squared plus
AB
something
squared.
AB.
plus b squared, but there's a middle term. It's not just as simple as distributing. What is the middle one?
AB.
2 times a times b. So it's 2ab. So it's the first thing squared plus 2 times the product of both of them
What do you do with C though?
plus the last term. Say it again.
What do you do with like C though?
With c,
Yeah.
what do you mean, like up here?
Yeah.
Oh,
What do you do with that?
okay. Don't make the connection between these a's and b's and those a's and b's. They're different.
They're different colors now.
They're different. Yeah. You'll see. You'll see where that comes from. Okay.
Because I kept missing that because I didn't understand why.
Okay, it'll show up. It'll show up in there. It's the last step. We'll get to that. So now, if we're just going to follow this pattern, look what happens here. So what's my A? Well, X, right? What's my B? 6, right? So what's A squared then?
X squared.
Okay, what's 2 times A times B? So that's 2 times X times 6. What's 2X times 6?
2x plus 6 squared.
12x, right? It's probably easier to think about it as being 2 times 6 times x, but you can multiply in any order, doesn't matter, right? So plus 12x plus b squared, well that's just 6 squared, what's that?
36.
Okay, so then, so x plus 6 squared just becomes x squared plus 12x plus 36. That's what all that stuff becomes. I've got to put it in parentheses though, how come?
Because it's times by 2/3.
Yeah, because I've got a 2/3 that's being multiplied by all that stuff, right? So what's the next step?
Multiply.
Multiply, divide, right? So then I got multiply, divide. In this case, I'm multiplying by what?
2/3.
2/3. So I'm just going to distribute the 2/3 to all the parts. So what's 2/3 times x squared?
2/3 x squared.
2/3 times 12 times x. What's 2/3 times 12?
8x.
8. Good. And we can do that easily. We can just say, okay, what's 12 over 3? That simplifies. 12 over 3 becomes 4 times 2 is 8. And then 2/3 times 36. Well, let's reduce first. 36 over 3 is 12 times 2. 24. And then finally at the end, now I get down to my last step, which is what?
Minus the 4.
Add, subtract. Good. So we're going to, should have had an S in there too. I didn't have my S in there. So then we're going to subtract the 4, right? We can, 24 minus 4 is just 20. So our final answer, that's bad color. Final answer looks like 2/3 x squared plus 8x plus 20. That's my answer, right?
That's a big question.
Yeah, it seems like a lot because we did a lot of talking, but it's not that big a deal. From the graph, we just have to find what h and k and a are, put it into vertex form, right? And then I'm just going to go through order of operations, regular top-down order of operations to simplify. And when I simplify something, I put it into its standard form. It could be a line. If we simplify a line, it just ends up in the form y equals, or f of x equals mx plus b, right? That's its, we call that slope-intercept form, but really it's like a standard form. Some number times x plus a constant. We'll do the same thing with cubic functions and quartic functions later in the year. It always works out to be, by simplifying, we get it into the easiest form, right, the standard form. Okay, so that's a little review. Now here's the thing, here's what I want to do for today. Okay, so we've got to kind of shift gears for a second. This is not hard though. I think this will be very helpful. So we already know how to do this, right? This is the section 3.5. The practices in section 3.5 have to do with this stuff, which is if we have a quadratic function like this, where we can point to a single x then we can isolate it by just reversing order of operations and working backwards, right? And you're getting some practice with that, getting good at it. You still need a little practice, I'm sure, but you're getting better at that. Okay, here's the next one though. How do we do something like this? Okay, this is different, right? This is real different because look what we got going here. I've got an X there and an X there. I can't point to a single X, and they can't be combined. They're not like terms. So I can't isolate the X to solve for it. I got to do something different, right? So here's the something different that we're looking at. We're gonna play a little game here. Who wants to make a little money?
Money?
Okay, right back here.
Oh, real?
All you, yeah, seriously, all you got to do.
Let's answer this question.
All you got to do, if this is, I'll give you all the money in my wallet. If you can tell me what one of these three numbers is, and here's the only stipulation is that the numbers behind each of these boxes have to multiply to that number. So the product of the three numbers is that number.
numbers or are they fractions?
I'm not telling.
You have to figure that out.
I feel pretty safe here, but go ahead and give me a guess.
You probably have nothing in your wallet.
How much money's on the table?
Boys,
Show us your
How much-
wallet first.
How much money's on the table?
He's like, it's Gucci.
I'll make it $10.
Any number? 26. Can you put any
26? Well, no, I got it right here. Carlos, what do you think?
Say like on the verge of 27, 26.
26?
26, 27, right out there.
Well, I got to know an exact number.
26.9.
26.9. Let's see if whoops, let's see if we have a
Wrong.
winner. Let's see if we have a winner.
Oh,
Oh!
Sorry.
Nobody got that right.
Sorry.
Wait,
You
does
haven't
anybody
had
actually
anyone
guess
ever
that?
get
You have also done
Wait, yeah.
1 times 1
wait.
times 724.
Yeah, you could, but those weren't. Okay, but listen. Okay, so the point is, you don't get to choose. I already chose the numbers. The point is, that was an impossible game for you guys, right? Because how are you going to know? There's nothing special about this number, right?
What happened if someone actually got it?
Okay, phone's away. I would have given them $10. Okay, Josh, you're next up for. I'm not going to give you money on this one. This is too easy. But I will give you. I'll pull out a fabulous gift or prize out of my drawer for you.
Is it like a
Same game. Same game. There are going to be 3 boxes, and I want you to tell me at least what one of the numbers is behind one of the boxes. Okay, that's all. I don't even care which box is behind. If you can pick one of the numbers, then you get a fabulous gift or prize.
This one's gonna be hard.
Because there's a lot of numbers.
Is it 0?
Say
What's
what?
that?
0? Is it
0 is the guess.
Wow.
Oh, bingo!
Hey!
There you go.
That's on me, bro.
All right, what do we got here? Let's see.
I think that deserves $5 at least.
Here, pack of batteries. There you go. I don't even know if it's complete.
Hey, I actually need these.
Okay, so now.
Hey, there's 2 in there.
Okay, there you go. Okay. Back to business. Okay, Josh, how did you know that the answer was going to be 0?
Anything
Didn't,
times 0
yeah.
is 0.
Yeah, the only way you can get a product to equal 0 is when you multiply by 0, right? Okay, that might seem like a simple thing, but in math, that's pretty important. We call it the zero product property. Okay? So in other words, if A times B equals 0, then for sure, either A equals 0 or B equals 0. And maybe they both do, right? But one or the other has to equal 0. If I had A times B times C equals 0, then we could extend that. Then either A is 0 or B is 0 or C is 0, right? Okay, that can be very useful for us, right? That can be useful in solving a problem like we just had. If I'm able to go from the problem we just had, if I'm able to somehow put that into a form like this, right? If I'm able to break that apart into a product of factors, and that process is called factoring, right? Where we can take an expression, take a quadratic expression like this in standard form, and we can break it apart into a product of 2 factors. That makes this pretty simple, right? Makes it simple because then all I have to do now, so let's just, don't even worry about what's behind my left hand and my right hand. I've got a factor behind my left hand and a factor behind my right hand. What has to be, phones need to be away please. What needs to be the value of either my left hand or my right hand for the product to be 0?
0.
1.
0. Either the left hand is 0 or the right hand is 0. It has to be, because the product is 0, right? So if I want to know what the solutions are, if I could get it from here down to there, and that's the process we need to practice a little bit, factoring. But if I could factor this expression, then now I know that either 2x plus 3 equals 0, right? Or x minus 5 equals 0, right? And those are easy to solve. You can solve those. This is a small equation that I can solve by isolating x. What are the 2 steps to get x by itself? Subtract 3, divide by 2. So what's the answer? Negative 3/2. Or, what about this one?
I can't see.
5/2.
5. See, if I could get it to there, it's easy, right? Okay, so then, what about, let's look at some examples. Real quick, I want to set this next one up just for a second. So a lot of times we want to find the zeros of functions. And sometimes people ask why that is. Well, here's one example. Let's say that we want to graph, let's say we've got a cannonball that we're launching out of a cannon. Could be a bullet out of a gun, could be a missile, could be anything, but a projectile. We're going to launch a projectile. If you launch a projectile up in the air, the path that it makes is parabolic. So it's a quadratic function is what describes that trajectory, right? Now, if it's a projectile, it starts at ground level, and let's say this is out in the salt flats in Utah or something, so it's absolutely flat ground. It's going to go up in the air and it's going to come down and hit the ground again. But if I extended that trajectory, it would just look like a parabola. Now, it doesn't go below the earth, but the shape does. You get what I'm saying?
Yeah.
So if we want to know, for example, let's say we knew what this function was for this particular trajectory, and that's one of the things we study in physics, right? Well, if we want to know how far it goes, all I've got to do is take the function and set the y value, which is the function, equal to 0, right? When we find the zeros of a function, well, all that means is we're plugging in 0, setting the function equal to 0, and solving, right? So we could do stuff like this, for example. If I want to find the zeros of this function, all I'm doing is just setting the function equal to 0 and solving. And it's already in factored form, so you guys can tell me the solutions, right? What are the zeros of this thing? When does it equal 0? When either x equals what? 9, because that would make the first factor 0, right? Or x equals
-1.
Okay, what about this one right here? If I set this one equal to 0. Well, 4, that factor can never equal 0 because it's 4. But this one can because it has a variable. What's the value of the variable that makes that factor 0? 4, 1. Okay, last one. What about down here? Okay, this, what's the value of x that makes that factor 0? How about this one? 0. 0. Right? So either x equals 0 or x equals 6 for that one. Okay, so our goal then is, how do we get from there to there? Okay? It's a really simple process. We'll review it real quickly. It's no big deal. Let's just try it. Just kind of warm up with just a couple little questions. Simple questions about signs of products. And this is important. You'll see why in a second. So what about this? If the product of two numbers is negative and the sum of the two numbers is negative, what are the signs of the two numbers? One's positive and one's negative, right? Because in order for them to multiply to a negative, we would have to have one positive and one negative. Which one's bigger if they add to a positive or add to a negative? The negative. Like, for example, -7 plus 4 is -3. They partially cancel, but there's a little bit of negative left over because that number was bigger, right? Okay, how about one like this? What if the product is positive and the sum is negative?
Two negatives.
Two negatives, right? They have to be the same sign to multiply to a positive, but if they're adding to a negative, they both must be negative, right? So both numbers are negative, okay? How about this guy? Product is negative and the sum is positive.
Positive.
One's positive.
One's positive and one's negative. Which is bigger this time? Positive, right? And then finally, you can probably guess which one this is. If both the product and the sum is positive,
Both numbers are
Both.
negative.
they're both positive, okay? So then, let's look at this now. So if we want to come up with, what we want to be able to do is we want to be able to take something like that and factor it, break it apart, okay? So we want this to look like, we want to turn this into something like x plus, let's just call it n sub 1 for number 1, times x plus n2 for number 2 equals 0. And then I could, easily find the solutions, right? That'd be a piece of cake. But I just need to find those magic numbers, n1 and n2, right? So what are the rules? Well, let's work backwards. What if I were going to start with something like this and multiply it out to put it in standard form? That gives us a clue. So here's the process, right? If we want to go from something like this to standard form, all I'm doing is just distributing. So if I distribute the x through, I'm just going to get x squared plus n2 times x. Now I'll distribute the n1 through, and I'll get n1 times x plus the product of n1 times n2, right? Now, I want that to match up. I want something times x squared plus something times x plus a constant. Well, this is the constant right here, isn't it? Right? And the number in front of x squared is just 1, right? But what's the number in front of x? Well, each of these terms has an x in it. So let's undistribute an x from both of those, and what's left over? n2 plus n1, but let's flip it around, n1 plus n2, right? So then that tells us that n1 plus n2, they have to add up to be b, right? The number in front of x. And they have to multiply to give you c. So that's our recipe for the magic numbers. The sum of the magic numbers is b, and the product of the magic numbers is c, as summarized right there, right? So if we're starting with something like this, where a is equal to 1, so we don't have a number in front of x squared, we have to just find those magic numbers. It's easy. Okay, so let's try that. Let's go back to this last example and see if we can do it. So what are going to be, what do my numbers have to multiply to here?
4 and 4.
So n1 times n2 has to equal what?
16.
16, right? They have to multiply to c. So that has to be true, and they have to add to what?
10.
10. So if they're going to multiply to a positive and add to a positive, they're both positive, aren't they?
8 and 2.
Right? Okay, so Blake, give me some, how am I going to figure this out then? If I want to make a table of n1 and n2, and then over here let's do their sum. What are factors? Let's start with big ones. What are factors of 16? I'll start you off. 16 times 1 would be 16, right? What do those add to? 16 plus 1 is
17.
17. Okay, too big, right? Move on down. What's the next one? 8 times 2, and what do those add to?
10.
Bingo, we got it, right? If we had kept going, we could have gotten 4 times 4, but that only adds to 8. So this is our winner right there, isn't it? Right? So our magic numbers are 8 and 2. So we can write this as x plus 8 times x plus 2. Now I put this into factored form, right? This is factoring. I just factored to get there. And so what would the solutions be?
Negative 8 to negative 2.
X, if this whole thing's equal to 0, either x equals negative a or x equals negative 2, right? Okay, let's try another. Let's try that one. So what do the numbers have to multiply to?
72.
Not 72.
Or negative 72.
Negative 72. And add to,
Negative 1.
okay, so what's that tell you about the signs?
There.
Positive and negative, and which one's bigger? We'll always make n1 the bigger number. Which would be? That could be the negative or the positive?
Negative.
Negative, okay. So let's go down our list here, and I want to show you a trend that's helpful. So if we put these numbers in, factors of negative 72, where the negative 1 is bigger. So we could do negative 72 times positive 1. What do they add to?
Negative 71.
Negative 71, way too big. You need to add to negative 1. Let's work down the list. Okay, so what about 2? 2 goes into 72 36 times. So we got negative 36 and 2, still way too big. 3 goes into 72 24 times, so negative 24 times 3, still too big. 4 times 18, right? 6 times 12. And then finally we get down to what? 8 times 9. That's it. Okay, look at the sums. These add to negative 34, negative 21, negative 14, negative 6, negative 1. What do you notice here? There's a trend. The closer together the two numbers are, the smaller the sum, right? The more extreme they are, the bigger the sum. So if we had started off with negative 36 times 2, we would have found that the sum is negative 34. That's way too big. So we know we got to get numbers closer together, right? See what I'm saying? So then what's this work out to be? It factors into x minus 9 and x
Plus 8.
Okay, and I guess I kind of brushed over this, but you see why those have to be x's, right? If I distribute x times x gives me my x squared. Those are freebies. It's the magic numbers that I have to find. I know the first term of each factor is going to be x as long as there's a 1 in front of x squared, right? Okay? And so if I wanted to solve this thing then, I would just get the solutions either x equals 9 or x equals negative 8, right?
Yep.
Okay, is that making sense?
Yeah.
Okay, try one more, then we'll call her good. Try that one. See if you can come up with that one on your own.
What does it equal to?
Yeah, what is it?
Well, I'll tell you what, we want, on the assignment, I don't even ask you this, I just want you to factor it. Yeah. So on the assignment, all I want you to do is fill in the blanks. Okay, we know these are x's. What do the magic numbers have to multiply to?
20.
Positive 20, so what about their signs?
They're both positive.
They're going to be the same sign. If they add to a negative, they're both negative. So what would they be?
One's negative.
So what numbers multiply to 20 and add to 12? Would they both be negative? 10 and 2. There it is. Right? Negative 10, negative 2. Right?
Get it.
You get it?
Wow.
You get it? Oh, it clicked.
Oh.
Okay. We're good.